Okay, so welcome to the second half of our lesson 2 in unit 3. So I paused between these strictly because we start getting into something a little bit more complex, but that doesn't mean that it's actually treated any different. It's just going to take a little bit more brain power because we're going to be using some more principles that we've learned in previous math classes. So you've worked with quadratic equations. That was a huge chunk of what you did in grade 11. So we're going to be pulling that back in addition to our work with trig functions and trig equations and the unit circle. So this is when I really do find that students benefit from that substitution method. So I'm going to do this first example using substitution. So again, I'm still asked for exact values, so I'm not using a calculator in my final answer. I'm working with radians again, so yay for me, because that's where my brain goes. But if you, again, think in degrees, you're welcome to think in degrees, but remember that final answer needs to be in radians. So I look at this and I'm like, oh my gosh, that looks so scary. So I say, let x equal tan theta. And by stating this, I can rewrite this statement. Now, a couple things that you need to know. Actually, one big thing is that when you see this statement, this actually means tan theta squared. We just don't write it like that. We write the square attached to the actual function so that people don't get confused and think that the theta is being squared. So just so you know, that's what that means. Which means instead of writing tan squared theta, I'm going to write x squared plus 5x plus 4 equals 0. This, to me, looks way less intimidating now that I don't have a trig function in there. Now, how do we solve quadratic equations? We deal with factoring if we can. So in this case, we do have the ability to factor. This would be x plus 4 and x plus 1 equals 0, which means that we've got two options, either x plus 4 equals 0 or x plus 1 equals 0, which means that x could be negative 4 or x could be negative 1. Because of this splitting, I'm going to have potentially more solutions than I did in our previous examples in the previous video, because I still need to go back and substitute back in. So again, highlighting that piece where I said that x equals tan theta, so I substituted x in for tan theta, but now I need to take it out again. So I can write tan theta equals negative 4 and tan theta equals negative 1. Okay, so I'm using exact values when possible. I have no idea when tan theta equals negative 4. That is not on my unit circle, so that's not happening with exact values. I'm going to have to use a calculator here. Okay, but I do know a time when tan theta could potentially equal negative 1 or 1, and that would be when, again, thinking back to the fact that tan theta is sine theta divided by cos theta. Therefore, I'm going to get 1 when these two are the same. Okay, so I'm going to need to use my calculator for here. I'm going to save that for after. Okay, so as a reference angle, sine theta over cosine theta would be happening, it would be 1 when the values are the same, and that happens at 45 degrees or pi over 4. So that's my reference angle. Okay. But tan is negative in quadrants 2, and again, you can always jot this out. All students take calculus. It's negative in quadrants 2 and 4. So in quadrant 2 and in quadrant 4, I'm going to have two solutions. So this would be pi minus pi over 4, or 3 pi over 4. And this would be 2 pi minus pi over 4, or 7 pi over 4. So those are two possible solutions. I'm then going to have to bust out my calculator for this, because I genuinely can't think of when on my unit circle I would create some sort of situation where I would be getting 4. So again, I'm going to have to go back in and make sure that I'm in radians, because that's the units my domain is given to me in. And then I'm going to do tan inverse of, and I'm just going to do 4, because again, I want my reference angle. So my reference angle is 1.3258. Now I can talk about, and again, it's negative, so I'm working in the same two quadrants that I did for my other possible solutions. So in quadrant 2 and quadrant 4, and I'm going to take pi minus this and 2 pi minus this to get my answers. So I'm going to use my calculator again to do that. Whoops. So again, measuring from my x-axis and going up, measuring from my x-axis and going counterclockwise. I'm subtracting in both of these cases, and these should be my two solutions for this one. So again, when it says exact values when possible, this was kind of like a gray area question. So this one would have had to have been on the calculator section, because there's no way I would have been able to evaluate this without using a calculator. So that's the strategy. Key thing to remember is, again, just like a quadratic equation, you're going to look to factor. So if you need to remember, I'm liking this fancy pen, and then remember also to sub back in. Okay, so those would be the two key things that we'd really want to remember to do. So if you go to the next question, it should actually be a little bit easier, strictly because we're dealing with cosine, but there's no extra number, so factoring should be a little bit easier. I would still personally choose to substitute in. So I won't do it that way, strictly so that I can show you what it looks like if you don't, but you are totally welcome to pause the video and try it using substitution as well. But if I don't use substitution, I look for what's in common. And I notice that there's a cos squared and a cos, which means that both terms involve cos theta. So I'm going to factor that out. And I'm left with cos theta plus 1. Make sure that looks like a theta. Equals 0, which means our options become either cos theta equals 0 or cos theta equals -1. And from here, I can 100% use exact values. These are on the unit circle, and I can talk about it in degrees. So cos theta, again, that's my x value on my unit circle. When x is equal to 0, that happens twice. It happens at 90 degrees, and it happens at 270 degrees. Over here, cos equals cos theta equals -1. That is when my x value is -1. That only happens once, and that's at 180. So those would be my two answers. I'm just going to make sure that that equal sign looks like an equal sign, not a less than or equal to sign. Okay, so it is possible to solve these quadratic equations involving trigonometric functions without using that substitution method that we used in example 7. But it's all about personal preference. And again, remembering that key piece of subbing it back in to solve for theta, not just solve for x, because a lot of people, and so you might want to choose a different variable instead of x, just because a lot of people, when they end up using x, we've been using x since we were in grade 9, grade 8 even, and when we get to having x isolated, our brain just kind of was like, this is a solid endpoint for a question. So something to bear in mind. You might choose a different letter. Okay, so example 9. This is another type of question. So we just dealt with a couple quadratics. Example 9 looks at when we have our kind of 3 inverse trig ratios. So just kind of as a reminder that when we talk about secant theta, what we're talking about is 1 over cos theta. And when we talk about cosecant theta, we're talking about 1 over sine theta. And finally, when we talk about cotangent theta, I find this is the easiest one, we're talking about the inverse of tan. Okay, so just kind of as a reminder that that's out there. So when I look at this, so using our inverse identities, so when I look at secant theta equals -2, what I'm really seeing is 1 over cos theta equals -2. From there, I can manipulate it so that I get cos out of the denominator and isolate it. So I'm going to end up with 1 over, and I'm going to put the negative out in front, 2 equals cos theta. And so once I have this statement, this is a statement that I can work with. This looks like something that I've worked with in the previous examples, in the previous video, and it's definitely on the unit circle. So with all that in mind, I can now say, well, I know my reference angle is for 1/2, and cos is 1/2 at, and again, I check my interval and it says it's in radians, so I'm going to look at that and be like, okay, that's pi over 3 as my reference angle, but I know that cosine is negative in quadrants 2 and 3, so that's where I'm going to work. So my final answer is going to be in quadrant 2 and in quadrant 3. Quadrant 2, I would be talking about 2 pi over 3, and in quadrant 3, I'm talking about 4 pi over 3. And again, measuring backwards and forwards from pi is how I generate those. So the same idea might happen here. I'm looking at it and I'm like, oh, that looks very, very intimidating, but I can maybe make it work from here. So I can, because it's already factored, I can break it apart and it's equal to 0. I'm going to break it apart into those two statements of each piece that's being multiplied could potentially be equal to 0 in order to produce 0 when it's multiplied. So I've got cotangent of theta is equal, or minus the square root of 3 is equal to 0, in which case cotangent of theta would be equal to the square root of 3. Working this one through, that means that it's 1 over tan theta is the square root of 3, or that tan theta is going to be 1 over root 3. And again, this is a value that is on my unit circle. It is something that I've used before. It's part of my special values. So working with that, again, that exact values. And with radians, I can consider that. I know that tan is positive in 1 and 3. So my reference angle, I have to look that up on my unit circle or remember my table of values, or wherever I'm going to get that from, is going to be pi over 6. And so that's one answer for quadrant 1 is pi over 6. And quadrant 3 is going to be 7 pi over 6. Again, measuring forward, adding it to pi. So those are two possible answers. I can't forget the other half of my multiplication statement though, so the other factor, which is the square root of 2 cosecant theta plus 2 equals 0. So if I isolate cosecant, that's going to be negative 2 root 2. Now, another thing that I can do here, and I can show it still by inserting my inverse relationship. So sine theta equals negative root, sorry, old habits die hard, negative 2 over root 2. But I need this to flip in order for sine to get out of the denominator. So I can also just take the reciprocal of the fraction on the other side. As long as I keep my rational statements the same, or my rational expressions the same, in terms of like top matches top, bottom matches bottom, they're in the same positions relative to the other one, I'm totally allowed to do that. So I'm just going to flip it up. So sine theta over 1, which we don't need to write, equals negative root 2 over 2. And again, we get to a point where I'm like, oh, I recognize that. It's on the unit circle. This is something I can manage. So again, sine is negative in quadrants 3 and 4. So I'm going to talk about my reference angle being, okay, just root 2 over 2, and that's in quadrant 1. And when I think about that, it's at pi over 4. So in quadrant 3, I say pi plus another pi over 4, which ends up being 5 pi over 4. And quadrant 4 is 2 pi minus pi over 4. And that leaves me with 7 pi over 4. And again, where that's coming from, if we're struggling with those fraction pieces, is I'm saying 2 pi minus pi over 4, which is coming from, which I'm going to try and get over a common denominator, which would be 8 pi minus pi all over 4, which is 7 pi over 4. So treating that pi almost as if it's a variable, like an x or anything like that. So those would be my answers for that question. Example 10, we're going to be using exact values when possible. If that's possible, we'll see quickly. And we're working in degrees. So we're going to use the same initial process where we want to try and get to a point where we can substitute those intervals in. So, oops. Or not the intervals, the identities. So we can break this apart, there we go, into secant theta minus 4 equals 0 and 5 cotangent theta minus 3 equals 0. From here, again, it's isolate to try and be able to plug things in. And again, that's a 5. Just being conscious it doesn't look like an S. So we get secant theta equals 4. So that's 1 over cosine theta equals 4, or cosine theta equals 1 over 4. Okay, and at this point, I recognize that I can't do an exact value. This isn't something I'm familiar with on my unit circle. There's no special angle that's associated with 1/4, so I will have to use my calculator for that. So I'm just going to isolate this one at the same time, see if I can do anything with it. So cotangent theta equals 3/5. Again, this is subtraction. Okay, and so then I recognize 1 over tan theta equals 3/5, or tan theta equals 5/3. So in both of these cases, these are not special angles, so I am going to use my calculator. Key things to remember is double check that your calculator is in degrees, And make sure you do your reference angle, and then always make sure that we're calculating all possible angles. So remembering that cos is positive in 1 and 4, and tangent is positive in 1 and 3. Okay, so again, reference angle, then stating our actual answers is going to be the goal. So at this point, I would strongly recommend you at least attempt this on your own calculator, strictly for the purpose of making sure we know how to punch things in. Make sure you know how to convert into degrees on your calculator instead of working in radians if it's not already there. So pause the video now and try it on your own. Again, making sure that that calculator is in degrees. I know when I started actually calculating these, I left my calculator in radians and it took me a second to catch myself. So these should have been our solutions. So we should have 4 solutions from, again, anything that's coming out of like what should kind of be like a quadratic equation is going to end up looking like this. So what does this mean for the next one? Well, this is a different type of question, actually. Example 11 looks at what we call kind of like multi-angles. So we see right away that we've got 2 theta in here. That's not supposed to be a square, that I forgot to put it as an exponent. We've got 3 theta down here. It means that we're going to actually be talking about considering things going multiple times around the circle. So when we are dealing with this, we can hypothetically talk about the angles as actually being like outside of a bigger interval. So when I go to solve, so the question is still asking the same thing. We're looking for exact values when possible on the interval 0 to 2 pi. So again, working in radians, switching back. The key thing here is that when I solve my initial angle, I'm going to account for 2 times my given domain. So I'm going to talk about actually 2 revolutions. Or twice as many as my interval allows. And you'll see why in a second, okay? The same thing happens here. My initial angle, or my initial solving maybe is a better way to word it. In this case would be 3 times the interval. And so in this case, that means I'm talking about 3 revolutions. Okay, so this is new. This is different than what we've been doing previously. But our approach will start out the exact same. So I'm still going to treat this whole function together and try and isolate it. So I'm going to move my 1 by subtracting, I'm going to move my 2 by dividing, so I'm left with the sine of, and I find I like to write it with brackets just to kind of help me remember that that 2 is attached to my angle. It's part of my angle value. Equals 1/2. Okay, and we know that this happens when my reference angle, or 2 theta r, is going to be when I'm talking about just 1/2. So when sine theta equals 1/2, that is at pi over 6. Okay, so at pi over 6. But it's negative, so I'm talking about in quadrants 3 and 4. And like I said, I have to account for 2 revolutions because I've actually got double my regular angle. So 2 theta could potentially be not pi over 6, because that's my reference angle and that's in quadrant 1, but looking at quadrant 3, measuring from pi plus pi over 6, that would be 7 pi over 6. And it could be 11 pi over 6 to get me in that fourth quadrant. Okay, but that only takes me one time around. I can actually also start talking about when I've gone past not only 2 pi, but 3 pi and a little bit. So that would be where your math comes in. I'm going to do some scratch work over here. 3 pi plus pi over 6 would be 3 times 6 is 18 pi plus pi over 6. Okay, so my additional options would be 19 pi over 6, and that would be 24 to go twice around. 4 pi minus pi over 6. This would get me 2 full revolutions around, but again, that's talking from here, and I measure backwards to end up in the fourth quadrant. So 4 pi minus this would be the same as 24 pi minus 1 pi over 6. So that would be 23 pi over 6. Okay, and that's great. This looks wonderful. You're like, okay, but why did we do this, Ms. Conrad, if my interval in the question is given to me as 2 pi? And so here is where it gets tricky. We are not done this question. We still need to isolate just theta. We are not done until we isolate that variable all on its own. So which means we still need to divide by 2. And we need to divide each of these by 2. So whichever way you want to think about it, multiplying it by a half or putting it as another denominator, or just multiplying your denominator by 2, whichever way makes the most sense for you to look at it. We need to eliminate this 2. So each of these is going to be divided by 2 again. So again, I'm going to do some scratch work over here so you can kind of see what that looks like in terms of process. So I've got 2 theta equals 7 pi over 6. Great. Divide by 2, divide by 2. That makes my left side nice and neat, but it makes my right side pretty ugly because I've got 2 denominators. Well, you can look at it as we're dividing by a whole number, so you multiply by the reciprocal, which is 1/2. Or you can look at it as, and that's really kind of like the best way to look at it, is 7 pi over 6 and then 1/2. So my numerator is not going to change, but my denominator now is going to be double what it was before. So instead of talking about 7 pi over 6, I'm actually talking about 7 pi over 12. Now, why does this need to happen? Again, it's because that 2 is attached to my angle inside my function. And so we see this in our graphs because this would be a compression of my period. And so I should expect when I graph sine of 2 theta, it would be that I would see 2 full periods in that time. And so I would expect twice as many potential values at any given point. So whereas a regular period, I'm seeing just 1. Now with a double angle, I'm talking about twice as much. So that's why we have to account for that 2 revolutions, because once I actually finish this question and I divide all of these by 2, what I'm going to end up is with my 7 pi over 12, but I'm also going to have 11 pi over 12 and 19 pi over 12 and 23 pi over 12. And you'll notice that this is technically less than 2 pi. So I know this is probably the most complicated thing that we've had to consider. But the idea is that because we had to divide by 2, we had to go around 2 revolutions, because then we then cut them in half. And we end up getting to within our expected interval, the interval that we were told we needed to work within. Okay, so we do fit the criteria in the end. We have to exceed it to start because we're dealing with double the actual value of theta. Okay, so all 4 of these are our answers. But we need to remember that whenever we're dealing with a multiple angle function, that's when we need to look at multiple revolutions of our trig functions. So you can give this one a shot on your own, or you can keep watching the video. I'm going to do a full explanation, but if you want to pause the video and then fast forward to the solution and see how you did, that's not a bad idea. Just the key thing here is because it's a triple angle instead of a double angle, we're going to take it 3 times the interval, or 3 full revolutions when I do that initial 2 theta equals. So when I do 3 theta equals here. Okay. So I look and I see cos theta equals, or cos of 3 theta equals root 3 over 2. And I know that in general, that means that for 3 theta, my reference angle is going to be pi over 6 again. So cosine is positive, and that happens in 1 and 4. So when I talk about 3 theta, I'm going to be talking about angle in quadrant 1, so pi over 6. And I'm going to be talking about 2 pi minus pi over 6, so that's 11 pi over 6. But that's only for 1 revolution. Then I've got to go around again. So I've got 13 pi over 6 and 23 pi over 6. And that is my second revolution. And finally, I'm going to have 25 pi over 6 and 6 times 6 is 36, minus 1 is 35 pi over 6, and that is for my third revolution. Okay, and again, we have to do this. We have to do 3 revolutions, because when I start dividing this by 3 to isolate my theta, I'm going to be starting to deal with a much bigger denominator, and so it should end up working out that I stay within that original stated interval in my question. So here I get pi over 18, 11 pi over 18, 13 pi over 18, 23 pi over 18, 25 pi over 18, and 35 pi over 18. And I want to double check that I haven't exceeded my interval, and I look here and I have not in fact exceeded my interval, because remembering that 2 pi as a denominator of 18 would be 36 pi over 18. So this checks out. I stay within my interval, and all of these are my possible solutions. So another way to think of it in terms of like what would you expect is that if you had just been given the equation to start with, cos theta equals root 3 over 2, you would have expected 2 solutions. Okay, but because we're dealing with a triple angle, we would expect 2 times 3 solutions. And that's what we get, 2 times 3, or 6 solutions. So that's another way to think about it in terms of helping you kind of wrap your head around it. Okay. So we will do some more practice questions like this. I will definitely find a worksheet that has multi-angle questions, because I find that that's definitely something that people struggle with. We're going to see that here again, working with degrees instead of radians. It's the same process, so if you want to pause the video at this point and give this a shot on your own, feel free to. But if you want to stick with me, you can also do that. So again, I'm going to look at this and I'm going to go, oh my goodness, I keep forgetting to do that. 2 revolutions. And I'm going to look at this, and I'm actually only going to look at half a revolution here. So I'm only going to look up to 180 degrees. And this is going to go up to, instead of 360, we're going to go to 720. So again, if I'm doing this as a reference angle, I would use my calculator, make sure it's in degrees, and I'd get a value. So it would be 58.2117 degrees. And from there, I would say that, okay, well then 2 theta would have to be, again, considering sine as positive in 1 and 2, it would be 58.2117, and then 180 minus that, 121 point. What's the rest of that? 783. And then I would go to the second revolution, so adding another 360 to this and adding 360 to that. So I would get these as my values for my second revolution. I then have to divide by 2, which means I'm dividing all of these by 2, treating them as all separate solutions. So theta could potentially equal half of all of these. Okay. So I get these answers. And what's nice about this is that it's very much more apparent than working in radians. I can clearly see that 240 does not exceed my original interval. So I can rest easy knowing that I've fulfilled that term in addition to solving for theta. So we can try again with this one. It's a little different because it's a half instead of a whole number, which means we're only going to actually go up to 180. We're only going to do half a revolution. So again, if I think about it in terms of regular unit circle references, cos results in √3/2 for pi/6, or because we're supposed to be working in degrees, we can talk about exact values as 30 degrees. And so then 1/2 theta, and again, we need to consider when is cosine positive. It's positive in 1 and 4, but we don't care about the bottom because we're only doing half a revolution. So we're only caring about quadrant 1. So I only would expect one solution, which is 30 degrees. To get rid of this, or to move it onto the other side, I could either multiply by 2 or divide by half, whichever makes more sense to you. And my final result is that I'm going to end up with 60 as my only solution. So that's an unusual situation where we actually have fewer solutions than we usually would. So example 13, our second last one, so bear with me, we're almost there, is looking at exact values again when possible. And in this time, they're giving us a different interval. So we've already seen a question like this. This is a quadratic, okay? And it's giving us infinities, which means we've actually got some flexibility. It hasn't said radians or degrees, so you can choose which one you're going to use. I personally am going to use radians because it's just kind of where I've ended up being more comfortable with. If you prefer degrees, you are more than welcome to work this through in degrees, and you could still check your answer. So all the steps up to the final solution are going to be the same, and it's just at the very end that things are going to change. So this is a good opportunity to pause the video and give this a shot on your own. So again, you can choose to do the substitution method, which was like let x equal sine theta, and sub it in. That's how I'm going to show my work, but you are more than welcome to also work through it using those trig functions in the equation. But pause the video, give it a shot, and I'll show my work so that you can kind of compare if we get different answers. Just a quick reminder, remembering that if we do this method of substitution in with x, to also make sure we plug our trig function back in to complete solving for theta. I've written the angles in degrees in green as well as the radians, just in case. So we are not done this question though because of the interval that they give us. So if it had been our standard like 0 to 2 pi or our standard 0 degrees to 360 degrees, we would be done. We would stop here, full stop. Great. But because they give us these infinities, we have to write what's called the general solution. And so I talked a little bit about this in our first unit. We saw it a little bit. The possibility of having like multiple options to choose from because these are periodic functions. So what we're going to see here is that all of these things can happen, and based on my period here, we're talking about sine theta, so it's just a regular old period. Every revolution that I land on these angles, every coterminal angle with these 1, 2, 3 possible answers, could give me another solution to this equation. So what does that mean? Well, it means that I can write 3 solutions, and they would look like this. I would start with 7 pi over 6, 11 pi over 6. So theta equals this, and theta equals pi over 2. But then I need to account for going around in a full circle. So I would say 2 pi, accounting for that full circle revolution to land there again. And then if you remember, we used the letter K to help us out here and simply state that K is an element of the integers. And what this allows us to do is that we're saying that K could be 0, it could be -1, it could be +1, it could be +100, but we're always going to be talking about full revolutions because we've written 2 pi, which is 1 revolution. So forwards or backwards, K is allowed to be negative or positive because it's an integer, but we can account for infinity that way. Because, again, those integers, would be anything from -infinity, includes 0, to +infinity, as long as they're whole numbers. Okay, so no decimal places. So that's pretty sweet. It means we can write a solution to account for all the points on my graph if my graph went on forever in both directions. All right, so we're on our last example. Bear with me, we're almost done. Okay. It says use algebra to solve the equation 7 plus 2 sine x equals 4 sine x plus 5 for negative, and this is really important, from -360 to 0. Then write the general solution. Okay, so we are first going to work within a very different interval. So we're just going to have to keep that in mind when we finally talk about our answer for x. But it doesn't change what we do to start. We're still going to do the same old math we've been doing. So we want to collect like terms, is what we've done previously. So I'm going to change the color on that one. Okay, so I'm going to collect my signs on one side of the equal sign, and I'm going to collect my constants on the other side. So I'm going to move the constants onto the left. So 7 minus 5 is 2. And I'm going to move 2 sine x over onto the right. So that's going to leave me with 2 sine x here. I'm going to isolate by dividing by 2 on both sides. And that leaves me with 1 equals sine x. And so x as a reference angle, or hypothetically, could be equal to, when sine is 1, which is, I'm working in degrees, so 90 degrees. Oh, shoot, before I continue. I could have written these general solutions as degrees as well, especially with what I'm kind of given in terms of my interval. So I could have also written it as 210 degrees plus 360 degrees times k, and theta equals 330 degrees plus 360, again a full revolution, and 90 degrees plus a full revolution times k. And we have to stipulate that k has to be a whole positive or negative number, so it has to be an integer. Sorry about that. So again, 90 degrees is my x, but I have to consider this. So it wouldn't actually be 90 that I would want to talk about. We're talking about here, this angle, but we're going to be measuring backwards, which is negative 270 degrees. So thinking back to that first unit we did again, and talking about like coterminal angles being both positive and negative, potentially. Now we have this. Again, we can write the general solution like we did up here. So going full circle, round and round, the general solution would then be negative 270 degrees plus 360 degrees of full revolution times k, where k is an element of the integers. Okay, so both of those would be included in my solution because it asks for both there. Use algebra to determine the general solution of this. Oh, sorry, there is one more example. This is a long video anyways. I'm glad I split it in two. Should have maybe split it in three. Okay, so finally, we're looking at this equation, another odd interval. Okay, set of real numbers, and list the roots in the domain of that. So again, this set of real numbers is another way of saying the general solution. In the same way that we're saying the interval negative infinity to infinity. Those are all the same thing. So we'll solve it. Cos of 3x equals negative 1. So that means that as a reference angle, so 3x, if I consider cos, would be negative 1. That's my x value on my unit circle, so that would be here. So because of this domain that I'm given, I'm not going to talk about it in terms of positive angles. I'm going to talk about negative angles. So that would be negative pi. And because it's a triple angle, I'm going to talk about it 3 times. So negative pi, negative 3 pi, and write that over here. 3 revolutions because multi-angle. It would be also negative 5 pi. And so x would be negative pi over 3, negative 3 pi over 3, which would also be just negative pi, and negative 5 pi over 3. And again, this all fits into the domain that I was originally given. Once I have those, again, when I go to write general solutions, so this would be my roots in the specific domain. My generals would be negative pi x equals negative pi over 3 plus 2 pi k, where k is an element of the integers. X equals negative pi plus 2 pi k, where k is an element of the integers. And finally, x equals negative 5 pi over 3 plus 2 pi times k, where k is an element of the integers. So it seems like a lot of writing to write out those solutions, but that now tells us any possible answer. So we can always check if someone else gives us a different solution, if it would still solve this equation. And if you're not sure and you're like, I'm not sure if this is really true, Miss Conrad, I want to double check, choose any value for k and actually test it. So if I chose for the first one that x equals negative pi over 3 plus 2 pi times negative 1. That's my value for k. So I simplify this. So I'm going to subtract 2 pi, which is 6 pi over 3. So that would leave me with negative 7 pi over 3 total. Okay, if I go to solve that in here now, what I would be doing is I'd plug in cos of 3 times negative 7 pi over 3 equals negative 1. 3's cancel out, so cos of negative 7 pi equals negative 1, and that's true. And we see that because, as we can see already, the trend is here that it's going to be all the odd negative pi values that produce a solution. So we are correct. You could punch it in your calculator if you weren't sure, but it does truly work. And the same with the other two. Now this is the last example. Da, da, da. You've been a champ for sticking with it so far. Bear with me a little bit longer. This one isn't too bad. Okay, so what you're going to do is first you're going to try and isolate x. So pause the video, try and use your strategies. If you want to use substitution, go ahead, but try and isolate x. What you're going to do is we're going to move that 2 over, so we end up with cos squared x, not theta. Careful not to switch your variables. Equals 1/2. But the tricky part of this question, again, because we have all these examples because there's so many variations of these equations, is that I want to get rid of that square, which means I want to introduce a square root. But when I introduce a square root, if you recall from last year, I don't know if that answer is positive or negative. So when I go to write my next line, I don't know if this is positive or negative. I just know that it's one or the other of 1 root 2, or if you want to convert it into rationalized radical, we'd be looking at that. Whichever one, both are perfectly acceptable. Okay, but we need that plus or minus because we introduced the square root, so we don't know whether it produced a positive or negative value. Both are equally viable options. So because of that, when we talk about our reference angle, we still talk about the positive, which cos producing root 2 over 2 happens at 45 degrees, based on my domain that I'm given. But this can potentially happen in all 4 quadrants. So I'm going to have 4 solutions to this because I have that plus or minus. So my positives happen here, my negatives happen here, but all of them are accounted for based on this. So when it's positive, I would expect 45 degrees. But then I'm also talking about 180 minus 45, which would be 135. Okay, I'd be talking about 225 and 315. And all of those are viable options. Again, all because we introduced that square root, so we have to account for both possibilities of a positive or a negative square root. So I know this was a lot. It's a huge amount of information. I'll be posting more homework practice questions to go along with it. For now, you should be able to find this one where you'll find we've got quadratics, we've got double angles, we've got inverse functions, we've got even cubics, So that's kind of an interesting one. If you get stuck on any of these, please be sure to ask. I'm going to create an answer key in here. So that's kind of my next project before I create lesson 3, because I think we're going to want to live in this a little bit just to really feel like experts. And the more comfortable you feel with these extra trig practice worksheets and these trig equations and manipulating them and solving them, the more comfortable you're going to be in the remainder of our unit, because it's basically all about being able to play with these different trig functions, mess around with them, and create one thing from another using different identities, which is a completely new concept, but still has to do with manipulating equations. So again, I'll be posting more practice for this. There will be an assignment posted as well, just looking at solving trig equations. And I strongly recommend that you do a ton of practice on these so that you get comfortable. Please note that you always want to check your intervals. A lot of the worksheets that I'm going to be posting are in radians, strictly because that's where most of the resources are. But do also notice that we are posting some very specific intervals here also. So just being conscious of that when you go to do your final answers. This part 1, solve for the unknown. Worksheet number 2 is just below it. So technically there's 2 worksheets in one here. This one might be a little bit more approachable actually to start with. So as much as it seems counterintuitive, you might want to start down here and then work your way up to the second one. But good luck, and please email if you have any questions. And if you want to meet in person to talk about this unit, I totally understand. It can be a little intense sometimes. It's a lot of information. And sometimes it's just easier to work through a couple problems in person. So just let me know if that's an option that you want to pursue.